Introduction and Chemistry 20 review. We're looking at drawing organic molecules today. Okay, let's start off with a warm-up question. Who wants to draw 4,5,7 trimethyl 2-decene 4,5-diol up on the whiteboard? Put your hands up. Somebody. Just, okay, well, nope. Then how about just give me 20 minutes or less and we'll take a look at this again. Organic molecules. What are they? Well, they are the molecules that make up all living things like plants and dinosaurs. And when a dinosaur dies, it's the oil that they turn into and the gas and the oil that we then use to make swanky Back to the Future shades and the plastic containers that we put our freezies inside of. And they also make up the artificial colors and flavors that are in the freezie and the Lego and t-shirts, which are mixed with cotton, which is another organic. And organics are also things like sugars and plastics. Did I mention that? Like this cool dog hat. And the dog itself is organic. And that stuff that gets stuck to the inside of your oven, that's organic as well. And the potatoes and squashes from this year's harvest, and the wood that was used to make the box for that, and grasshoppers, there's a weird bug, and all that stuff that I tried to pack into the back of my SUV, while the majority of that stuff was made out of organic molecules. There are over 9 million known organic molecules. Typically, organic molecules are those that contain carbon and hydrogen. This includes anything that is living, that was living, or was derived from molecules that were made by living organisms. This includes such things as people, dinosaurs, plants, animals, plastics, oil, gasoline, and rubber, and on and on. So dinosaurs, they died, they turned into oil. Oil we then turn into Star Wars action figures. So many organic molecules exist because carbon can link to one another and form extremely long carbon chains. Organic molecules occasionally include other elements such as oxygen, nitrogen, bromine, chlorine, sulfur, and potentially other elements. When we draw our organic molecules, they will only consist of carbon, hydrogen, and oxygen. Two molecules that have the same chemical formula but are arranged differently are known as isomers. One example of an isomer is octane and 4-methyl-heptane. They both have the chemical formula C8H18. But since they are bonded differently, they will have different physical properties. For example, these two molecules have different melting points and they have different boiling points from one another. Differences between organic and inorganic molecules. Well, organic molecules do not usually dissolve easily in water, which is a good thing because that means styrofoam cups would dissolve when you put your coffee inside of them. Organics decompose in heat easily, and you've seen that when you've put plastic in a fire at some point. And organic reactions like photosynthesis generally take a long time. That's why it takes so long to grow that garden. Since some organic molecules have similar structures, arrangement of atoms must be determined through experimentation. So you compare the chemical and physical properties. When conducting organic experiments, a number of products are usually produced. In order to get a high percentage of a specific product, the temperature and pressure must be carefully monitored, and catalysts are often used. Remember from grade 10? Catalysts are things that speed up reactions but are not used up in the reaction. Organic molecules are covalently bonded but are not often polar molecules. Organic molecules are usually so large that any polar bond that might be present isn't strong enough to cause the molecule to really move around. So in something like caffeine, the oxygens are pulling on the carbon's electrons, but the molecule is so large that caffeine doesn't really move too much. We'll talk more about polar bonds later in the unit. Drawing organic molecules. An organic prefix is used to identify the number of carbon atoms that have formed a chain. We are going to be using the organic numbering that is found on your formula sheet. Meth is 1, eth is 2, prop means 3, but means 4, pent means 5, and so on. Carbon atoms make 4 bonds, so hydrogen is added to fill in the rest of the carbon bonding potential. If we see that a carbon is only making 3 bonds, then we'll add a hydrogen to that carbon because all carbons make 4 bonds. An ane ending identifies that there are only single bonds between the carbon atoms. The general formula for alkanes is CnH2n plus 2. So whatever our number of carbons are, our number of hydrogens will be double that number plus 2. I want you to add to your formula sheet that ane means single bond. Now let's say we have methane. Meth, on our organic prefix, it says that meth means 1. So I have 1 carbon. And ane means single bond. So I've got 1 carbon with single bonds. Now, all the bonding potential of the carbon has to be made up by hydrogens when we're finished. So we have a carbon here that's making no bonds, and all carbons have to make 4 bonds. So I will then add 4 hydrogens to that carbon. And that is the formula for methane. Let's say I have ethane. Eth means 2 carbons. Ane means singly bonded. So I have 2 carbons singly bonded. And again, all the carbons have to make 4 bonds. Carbon is only making 1 bond currently, so I will add 3 hydrogens to each carbon. And that's the formula for ethane. And if I have propane, prop means 3 carbons. Ane means singly bonded. So I draw 3 carbons singly bonded. The first carbon will require 3 hydrogens, so it's making 4 bonds. The second carbon is already making 2 bonds, so I have to add 2 hydrogens to it. And the last carbon will need 3 hydrogens added to it. And that's the formula for propane. An ene ending identifies a double bond between 2 carbons. The general formula of an alkene, if that molecule contains 1 double bond, is CnH2n, meaning the molecule has twice as many hydrogens as the number of carbons. Methane can't exist since meth means 1 carbon. And if I need to put a double bond between 2 carbons, obviously I can't do that if I only have 1 carbon. I want you to add to your formula sheet that ene means double bond. So if I look at ethene, eth means 2 carbons. So I'll draw 2 carbons. And ene means double bond. So I'll put in a double bond. Now the first carbon is already making 2 bonds, so I will give it 2 hydrogens. And the second carbon also making 2 bonds, so it needs 2 hydrogens. And that is the formula for ethene. If I have propene, prop means 3, so I have 3 carbons. So 1, 2, 3 carbons. And ene means double bond, so I put in a double bond. Now the first carbon is making 2 bonds, so it needs 2 hydrogens. The second carbon is already making 3, so I add 1 hydrogen to either the top or the bottom, it doesn't matter. And the last carbon is making 1 bond, so I will add in 3 hydrogens. Alkyne, the YNE ending identifies the presence of a triple bond between carbon atoms. So on your formula sheet, note that YNE means triple bond. So if I have ethyne, eth means 2 carbons. So I draw 2 carbons. Yne means triple bond. So I put in a triple bond. And each carbon is already making 3 bonds, so I will add 1 hydrogen to both sides. And that's ethyne. Propyne, prop means 3, so I have 3 carbons. 1, 2, 3. Yne means triple bond, so I'll put in a triple bond. So the first carbon needs 1 hydrogen. The middle carbon is already making 4 bonds, so it gets no hydrogen. And the last carbon needs 3 hydrogen so that it is making 4 bonds. And that's propyne. Single exceptions to the parent chain. The parent chain is the longest chain of carbons in the molecule. So we're going to start with 2-pentene. What's with the number? Well, there is more than one location where the double bond could go. So a number is used to identify its location. So we look up pent. Pent means 5, so we draw out 5 carbons. 1, 2, 3, 4, 5. Ene means double bond, and that double bond is going to go on the second carbon. So I number my carbons, and I place it on the second carbon. Now I add in my hydrogens so that each carbon is making 4 bonds, and that's 2-pentene. An OL ending signifies the molecule is an alcohol. This means an OH is attached to the molecule. So if I have 2-pentanol, pent again means 5, so I draw 5 carbons. 1, 2, 3, 4, 5. AN means single bond, and OL means we have an OH, and it's going to be located on this second carbon. So I number my carbons, and on the second carbon, I place an OH. Now I go around and make sure that all my carbons are making 4 bonds by adding hydrogen. And that's 2-pentanol. Alkyl groups are smaller chains attached to the parent chain. They use an organic prefix to identify the length, and their name ends in YL. On your formula sheet, make a note that YL means small attached carbon chain. So if I have 2-methylpentane, pent means 5, so I have 5 carbons. Ane means singly bonded, and methyl means a 1-carbon chain, and that goes on the second carbon. So I put a 1-carbon chain on my second carbon. Then I fill in the rest of the carbons with hydrogen, so they are all making 4 bonds. Pentadiene. Note, commas are placed between series of numbers. You may have noticed dashes are placed between numbers and letters, and that covalent prefixes are being introduced. Covalent prefixes are used if we have more than one double bond, if we have more than one alcohol, or if we have more than one attached carbon chain that is of the same length. So if I had 2 methyls, it would have to say dimethyl. So let's look at this name. Pent means 5, so I have 5 carbons, so I will draw out 5 carbons. Di means 2. And ene means double bond. So I have 5 carbons. There are 2 double bonds. And the double bonds will go on the first and third carbon. So I will number my carbons. And I will place a double bond on the first carbon and the third carbon. Now I add hydrogens to make sure that every carbon is making 4 bonds. And that is 1,3-pentadiene. 2,2-pentaneediol. Again, pent means 5, so I have 5 carbons. So 1, 2, 3, 4, 5 carbons. Ane means singly bonded, di means 2, and OL means alcohols. So 5 carbons singly bonded with 2 alcohol groups. The OHs are going to go on the second and second carbon. So I number my carbons, and I place 1 OH on the second carbon, and I place another OH on the second carbon. Now I add hydrogen so that each carbon is making 4 bonds. And that's 2,2-pentaneediol. 2,2-dimethylpentane. Pent again means 5, so I have 5 carbons, and ane means singly bonded, so 5 carbons singly bonded. So 1, 2, 3, 4, 5 carbons. Then I have di, which means 2, so di means 2, and meth means 1, so I have 2 1-carbon chains. And those are going to go on the second and second carbon. So I number my carbons, and I place a methyl group on the second carbon and another methyl group on the second carbon. Then I fill out the rest of my carbon's bonding potential with hydrogens so that each carbon is making 4 bonds. And that's 2,2-dimethyl pentane. Now before we move on, I want to point this out because a lot of people say, why can't I do this? Isn't this 2 1-carbon chains? But this is 1 2-carbon chain. This wouldn't be a methyl, this would be an ethyl because the carbon chain that's attached is a 2-carbon chain. 2,3-pentane-diol. Again, pent means 5, so I have 5 carbons. So I draw out 5 carbons. Ane means they're singly bonded, which is good because that's what we have. Di means 2, so I have 2 OLs, and OL is alcohol. So I have 5 carbons singly bonded with 2 alcohols, and those alcohols this time are going on the second and third carbon. So I number my carbons, and I put an OH on the second carbon, and I put an OH on the third carbon. Now, I put one on the top, one on the bottom. It doesn't really matter if I put them both on the top, both on the bottom, or had put the first one on the bottom, third one on the top. Doesn't matter, just as long as I have an OH attached to the second and an OH attached to the third. And then I fill in the rest of carbon's bonding potential with hydrogens, and that gives me 2,3-pentane-diol. 2,3-dimethylpentane. Again, pent means 5, so I have 5 carbons, and ane means singly bonded, so 5 carbons singly bonded. So 1, 2, 3, 4, 5. Di means 2, and meth means 1. So I have 2 1-carbon chains, and they're going to go on the second and the third carbon. So I'll number my carbons. I'll put a single carbon on the second and a single carbon on the third. And then I fill in the rest of carbon's bonding potential with hydrogens. And now I have 2,3-dimethylpentane. 3-ethyl-2-heptanol. Hept means 7, so I have 7 carbons, and ane means single bonds. So I'm going to draw 7 carbons with single bonds. Then I have eth, and eth means 2, and YL means smaller carbon chain. So I have a 2-carbon chain that is going to be attached to my third carbon. So I'll number my carbons, and on the third carbon in, I will place a 2-carbon chain. I also have OL, which means alcohol, and that will go on the second carbon. So second carbon in, I will put an OH. And now I will fill in the rest of carbon's bonding potential with hydrogens, and that is 3-ethyl-2-heptanol. 2-methyl-2-hexene. Hex means 6. So I've got 6 carbons. So I will draw 6 carbons. And then I've got meth, which means 1 carbon. And that is a 1-carbon chain that goes on the second carbon. So I'll number my carbons. And on the second carbon in, I will put a methyl group. I also have ene, which means double bond. And that's going to also go on the second carbon. So after the second carbon, I will place in a double bond. Then I will add hydrogens to each carbon so that each carbon is making a total of 4 bonds. And that's 2-methyl-2-hexene. 5-heptene-2-ol. Now numbering for alcohols and double bonds both come before the parent chain. If both are present in the same molecule, the number associated with the alcohol is then placed just prior to the OL ending in order to avoid confusion. I have hept. Hept means 7, so I have 7 carbons. So I draw out 7 carbons. I have ene, which means double bond, and that's going to go on the 5th carbon. So I number my carbons and place a double bond at the 5th carbon. I also have OL, which means I have an OH group, and that goes on my second carbon. So second carbon in, I place an OH. And now I go through the molecule and make sure that each carbon is making 4 bonds by adding hydrogens to the carbons that need more bonds. And that's 5-heptene to all. Multiple alkyl groups. So if I've got a methyl group, ethyl group, and propyl group all in the same molecule, they get listed alphabetically. So ethyl gets listed first, then methyl, then propyl. And even if I have a covalent prefix, let's say I've got 2 methyls, so it becomes dimethyl, it still gets listed after ethyl. So regardless of covalent prefix, ethyl groups are always listed before methyl groups, which are always listed before propyl groups, alphabetically. 3-ethyl, 2,3-dimethyl heptane. Hept means 7 carbons. So I have 7 carbons, and ane means singly bonded. So I draw 7 carbons singly bonded. I see eth with a YL ending. So I've got a small carbon chain, and eth means 2. So I have a 2-carbon chain attached to the 3rd carbon on my long chain. So I count out my carbons, and on the 3rd carbon, I put in my 2-carbon chain. I also have di, which means 2, and methyl, YL meaning small carbon chain, meth means 1 carbon. So I have 2 1-carbon chains I have to add to my parent chain. They're going to go on my 2nd and 3rd carbon. So I put a single carbon on my 2nd and a single carbon on my 3rd carbon. And then I fill in the rest of my bonding potential for the carbons with hydrogen to make sure every carbon has made 4 bonds. And now multiple alkyl groups. This might look familiar. We got that 4,5,7 trimethyl to decene 4,5-diol from the beginning. So let's break it down. Dec means 10. So I've got 10 carbons. So I'll draw out 10 carbons. And then I've got ene. Let's do that next. Ene means double bond, and that double bond has to go on the 2nd carbon. So I'll number all my carbons, and after the 2nd carbon, I will put in a double bond. Looking at the front, I've got tri. Tri means 3, so 3, and meth means 1 carbon. So I have 3 1-carbon chains going on 4, 5, 7. So I put on 4, 5, and 7. I also have at the back end di, which means 2, and OL, which means OH, an alcohol. So I have 2 alcohols, and the OHs have to go on the 4th and 5th carbon. So I put an OH on the 4th carbon and then the 5th carbon. And that's the whole name. So I just got to fill out my hydrogens to make sure all the carbons are making 4 bonds. So 3 on the 1st carbon, 2nd carbon needs 1, 3rd carbon needs 1, 4th has 4 bonds, the 5th carbon has 4 bonds, the 6th carbon needs 2 hydrogens, 7th needs 1 hydrogen, the 8th needs to make 2 more bonds, 9th needs to make 2 more bonds, and the 10th needs to make 3 more bonds. And there you have it. Not that tough, is it now? 4,5,7 trimethyl, 2-decene, 4,5-diol. Rolls off the tongue. So you have this period and the next period to work on the assignment. If you finish that up inside of class time, I encourage you to go on to the next assignment and attempt to start naming these.